Multiwire branch circuits, often abbreviated as MWBCs, consist of two or more unrounded conductors that share a common neutral conductor. These circuits are specifically designed to supply only line to neutral loads. Understanding the nuances between different types of circuits is crucial for proper electrical installations and adherence to safety standards. Let's clarify the distinctions between a 3-wire circuit and a multi-wire branch circuit. A standard 3-wire circuit comprises one phase conductor, one neutral conductor, and one equipment grounding conductor. In contrast, a multi-wire branch circuit includes two or more phase conductors, one neutral conductor, and one equipment grounding conductor. The key difference lies in the number of phase conductors sharing a single neutral. Now, let's address the difference between a 4-wire 3-phase circuit and a multi-wire branch circuit. A 4-wire 3-phase circuit consists of 3 phase conductors, one neutral conductor, and one equipment grounding conductor. This type of circuit is capable of supplying both line-to-line and line-to-neutral loads. However, a multi-wire branch circuit is limited to supplying only line-to-neutral loads. This distinction is vital when designing electrical systems for various applications. Derating is an important consideration when dealing with multi-wire branch circuits, especially when the load exceeds 20 amps. In this specific scenario, involving 9 circuits each with a 20 amp load, the question arises regarding the appropriate wire size. Based on standard practices and electrical codes, a number 10 American wire gauge, abbreviated AWG, wire should be used for these circuits. Now let's delve into the concept of unbalanced neutral currents within multi-wire branch circuits. The neutral conductors in a multi-wire branch circuit carry the unbalanced current of all the current-carrying phase conductors. This means that the neutral conductor shared by the most current-carrying phase conductors will carry the highest unbalanced current. Given the circuit configuration provided, where circuits 1, 3, N, 2, 4, 6, N, 8, 10, 12, N, 7, and all feed receptacles, certain neutrals will carry unbalanced current. Specifically, the neutrals following 2, 4, 6, 8, 10, and 12, as well as the neutral following 7, will carry unbalanced current. This is because these neutrals are shared by multiple current-carrying phase conductors. To elaborate further, consider a multi-wire branch circuit with two 120-volt circuits sharing a neutral. If one circuit draws 10 amps and the other draws 8 amps, the neutral will carry the difference, which is 2 amps. However, if both circuits draw 10 amps, the neutral will theoretically carry 0 amps. In a 3-phase multi-wire branch circuit, the neutral current is more complex to calculate, but it is always the vector sum of the phase currents. For example, imagine a 3-phase 4-wire system with line-to-neutral loads. If phase A carries 15 amps, phase B carries 12 amps, and phase C carries 10 amps, the neutral current would be the square root of the quantity 15 squared plus 12 squared plus 10 squared minus 15 times 12 minus 15 times 10 minus 12 times 10, which equals approximately 8.7 amps. Now, consider the implications of derating due to the number of current-carrying conductors. The National Electrical Code, commonly called the NEC, addresses this in Table 310.15. For example, if you have 4 to 6 current-carrying conductors in a raceway, the allowable ampacity of each conductor must be reduced to 80%. If you have 7 to 9 current-carrying conductors, the ampacity must be reduced to 70%. This derating factor is applied to prevent overheating of the conductors. Let's apply this to the scenario with the number 10 American wire gauge wire. A number 10 American wire gauge wire typically has an ampacity of 30 amps at 75 degrees Celsius. However, if we have 7 to 9 current-carrying conductors, we must reduce the ampacity to 70% of 30 amps, which equals 21 amps. Since each circuit is designed for a 20 amp load, the number 10 American wire gauge wire would still be adequate after derating. When installing multi-wire branch circuits, it is crucial to properly identify and label the neutral conductors. This helps prevent accidental overloading of the neutral and ensures safety during maintenance. It is also important to use the correct type of overcurrent protection for each circuit. Circuit breakers or fuses should be sized appropriately to protect the conductors from overload and short circuit conditions. Consider the scenario where you have multiple multi-wire branch circuits in a single panel. It is good practice to separate the neutrals for each circuit to minimize the risk of neutral current imbalance. This can be achieved by using separate neutral bars or by clearly labeling and isolating the neutral conductors. In addition to the NEC, local electrical codes may have specific requirements for multi-wire branch circuits. It is essential to consult these local codes to ensure compliance and safety. Remember, electrical work can be dangerous, and it is always recommended to consult with a qualified electrician when dealing with multi-wire branch circuits or any other electrical installation. They can provide expert guidance and ensure that the work is done safely and correctly. Now let's think about a situation where we're using a multi-wire branch circuit to supply lighting loads. It is important to distribute the lighting loads evenly across the phase conductors to minimize neutral current. This can be achieved by carefully planning the circuit layout and balancing the number of fixtures connected to each phase. In some cases, it may be necessary to use a larger neutral conductor than the phase conductors to accommodate the anticipated unbalanced current. This is especially important in situations where there are significant differences in the loads connected to each phase. For example, in a commercial building with a mix of lighting, receptacles, and equipment, the neutral conductor may need to be sized larger to handle the unbalanced current. Furthermore, it is also essential to consider the voltage drop in multi-wire branch circuits, especially over long distances. Excessive voltage drop can cause equipment to malfunction and can also lead to inefficient operation. To minimize voltage drop, it may be necessary to use larger conductors or to install additional circuits. The NEC provides guidelines for calculating voltage drop and recommends that the voltage drop should not exceed 3% for branch circuits and 5% for feeders. Now let's consider a scenario where you're using a multi-wire branch circuit to supply electronic equipment. Electronic equipment is often sensitive to voltage fluctuations and can be damaged by excessive neutral current. To mitigate these risks, it is recommended to use dedicated multi-wire branch circuits for electronic equipment and to ensure that the neutral conductor is properly sized and grounded. In addition, it is also important to use surge protection devices to protect electronic equipment from voltage spikes and surges. Consider the impact of harmonics on multi-wire branch circuits. Nonlinear loads, such as electronic ballasts and variable frequency drives, can generate harmonic currents that flow in the neutral conductor. These harmonic currents can cause the neutral conductor to overheat and can also interfere with the operation of other equipment. To mitigate the effects of harmonic currents, it may be necessary to use harmonic filters or to increase the size of the neutral conductor. The NEC provides guidance on dealing with harmonic currents in electrical systems. Think about the importance of proper grounding in multi-wire branch circuits. Proper grounding is essential for safety and to prevent electrical shock hazards. The equipment grounding conductor provides a low impedance path for fault current to flow back to the source, which helps to trip the overcurrent protection device. The NEC specifies the requirements for grounding electrical systems and equipment. Also consider the use of ground fault circuit interrupters, abbreviated GFCIs, in multi-wire branch circuits. GFCIs are designed to detect small amounts of current leakage to ground and to quickly interrupt the circuit. GFCIs are required in certain locations, such as bathrooms, kitchens, and outdoor areas, where there is a higher risk of electrical shock. Think about arc fault circuit interrupters, abbreviated as SIs, which provide additional protection against electrical fires. SIs are designed to detect arc faults, which are dangerous electrical conditions that could cause fires. SIs are required in certain locations, such as bedrooms, to protect against electrical fires. Now let's consider the use of isolated ground receptacles in multi-wire branch circuits. Isolated ground receptacles are designed to provide a separate grounding path for sensitive electronic equipment. The grounding conductor for an isolated ground receptacle is not connected to the metal box or conduit, which helps to reduce noise and interference. Isolated ground receptacles are often used in computer rooms and other areas where clean power is essential. Consider the coordination of overcurrent protection devices in multi-wire branch circuits. It is important to coordinate the overcurrent protection devices to ensure that the smallest fault current will trip the nearest overcurrent protection device. This helps to minimize the extent of the outage and to prevent damage to equipment. The NEC provides guidance on coordinating overcurrent protection devices. Also think about the importance of regular maintenance and inspection of multi-wire branch circuits. Regular maintenance and inspection can help to identify potential problems before they become serious. This includes checking for loose connections, damaged insulation, and other signs of wear and tear. It is also important to test GFCIs enough size regularly to ensure that they are functioning properly. And consider the documentation of multi-wire branch circuits. Proper documentation is essential for future maintenance and troubleshooting. This includes keeping accurate records of the circuit layout, conductor sizes, overcurrent protection devices, and other relevant information. The documentation should be kept in a safe place and should be readily available to qualified personnel. Furthermore, let's consider energy efficiency when designing and installing multi-wire branch circuits. Using energy-efficient lighting and equipment can help to reduce energy consumption and save money. It is also important to properly size the conductors to minimize voltage drop and energy losses. The NEC provides guidance on energy-efficient design practices. Remember that safety is paramount when working with electricity. Always follow safe work practices and wear appropriate personal protective equipment. If you are not qualified to perform electrical work, consult with a qualified electrician. Now let's delve into more advanced considerations for multi-wire branch circuits. In large commercial or industrial facilities, multi-wire branch circuits are often used to distribute power to a variety of loads. In these applications, it is especially important to carefully plan the circuit layout and to properly size the conductors and overcurrent protection devices. It is also important to consider the potential for harmonics and other electrical disturbances. In some cases, it may be necessary to use specialized equipment, such as harmonic filters or power conditioning units, to mitigate these disturbances. For example, in a data center, multi-wire branch circuits are used to supply power to servers and other critical equipment. In these applications, it is essential to ensure that the power is clean, reliable, and free from disturbances. This requires careful planning, proper installation, and regular maintenance. Similarly, in a hospital, multi-wire branch circuits are used to supply power to life support equipment and other critical systems. In these applications, it is essential to ensure that the power is available at all times. This requires redundant power sources, backup generators, and uninterruptible power supplies, abbreviated UPS. It is also important to regularly test and maintain these systems to ensure that they are functioning properly. Consider the use of smart circuit breakers in multi-wire branch circuits. Smart circuit breakers provide advanced monitoring and control capabilities, such as remote tripping, current monitoring, and energy metering. These features can be used to improve energy efficiency, reduce downtime, and enhance safety. Smart circuit breakers can be integrated into building automation systems to provide real-time data and control. In addition, let's consider the use of power quality meters in multi-wire branch circuits. Power quality meters can be used to monitor voltage, current, harmonics, and other electrical parameters. This data can be used to identify potential problems and to optimize the performance of the electrical system. Power quality meters can also be used to verify compliance with industry standards. Think about the future trends in multi-wire branch circuits. As technology advances, we can expect to see more sophisticated and intelligent electrical systems. This includes the use of solid-state circuit breakers, wireless monitoring systems, and advanced energy management software. These technologies will enable us to create more efficient, reliable, and safe electrical systems. Always remember that the NEC is constantly evolving to keep pace with technological advancements and to address emerging safety concerns. It is important to stay up to date with the latest code requirements and to follow best practices when designing, installing, and maintaining multi-wire branch circuits. In summary, multi-wire branch circuits are a versatile and efficient way to distribute power to a variety of loads. By understanding the principles of operation, following the NEC requirements, and using best practices, you can ensure that these circuits are safe, reliable, and energy efficient. Electrical theory is no match for common sense and practical experience.